Alright, you guys, if you could please turn to 2.2. It's right after the sandwich theorem that we learned last time. Alright, horizontal asymptotes. You guys kind of already know what horizontal asymptotes look like. They look something kind of like this, right over here. This dotted line is a horizontal asymptote. This graph gets closer and closer and closer and closer to that asymptote as x approaches infinity, but it never quite gets there, okay? So here's the definition. The line y equals b is a horizontal asymptote of the graph of y equals f of x if either the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. So for example, over here, the limit as x approaches infinity equals, I don't know, maybe -1 or -2, whatever this line is here. The graph could go the other way, and as x approaches negative infinity, it would be the same case, another horizontal asymptote. Alright, let's do an example. Example 1. Use graphs and tables to find the limit as x approaches infinity of f of x, the limit as x approaches negative infinity of f of x, and identify all horizontal asymptotes of f of x equals x over the square root of x squared plus 1. Alright, I've pulled out my calculator here. Let's graph the function and take a look. There we go. Okay, and we can change the window here if we want. Alright, I'm going to change the Y. There we go. Alright, so already we can kind of see that there are two horizontal asymptotes going on here. Alright? Alright, it's clear that the limit as x approaches infinity, that it's getting closer and closer to the line y equals 1. As x approaches negative infinity, it's getting closer and closer to the line y equals -1. So let's go ahead and write that down. Alright? Therefore, the limits are, the horizontal asymptotes are y equals 1 and -1. And usually I just call these HA for horizontal asymptotes. There we go. Alright, go ahead and pause the video here and try this one. Alright, this is the answer you guys should have gotten. Let's go on to the next page. Example 2. Find the limit as x approaches infinity of f of x for f of x equals sine of x over x. Alright. We are actually going to be using the sandwich theorem for this one. If you guys remember, the sandwich theorem basically says if you can prove that a function is in between two other functions that have the same limit, then this function has to have that limit also. Now, we know that sine is in between 1 and -1. If you guys remember the graph of sine, it moves kind of like this, right? And it bounces back and forth between -1 and 1. Let's go ahead and write that down. Alright. So, if sine is in between 1 and -1, if you were to take this inequality here and divide all three terms by x, this is what you would get. Sine of x over x is in between -1 over x and +1 over x. So, let's take the limit of this and of this and see if they're the same. Alright, the limit as x approaches infinity of -1 over x, basically as x in the denominator gets bigger and bigger and bigger and bigger, this fraction is going to get closer and closer to 0. And the same thing with this one. 1 over x, as x gets bigger and bigger and bigger and bigger and bigger, the fraction is going to get closer and closer and closer to 0. Okay, so both of these equal 0. So because this equals 0 as x approaches infinity, and this also equals 0 as x approaches infinity, because sine of x over x is in between those two functions, it also has to equal 0. Okay, there we go. Okay, go ahead and pause the video here and try this one. Alright, this is the answer you guys should have gotten. Basically, I took this fraction. We know that cosine is in between -1 and 1, and I split the fraction up into two fractions, 1 over x squared and cosine x over x squared. 1 over x squared, we already know that equals 0. This is the one we have to find. Now, if cosine is in between negative 1 and 1, kind of like what we did over here with sine, we can put it in between negative 1 over x squared and positive 1 over x squared. And since both of those equal 0, this equals 0 also. So if the limit as x approaches infinity of 1 over x squared equals 0, and the limit as x approaches infinity of cosine x over x squared equals 0, then together it's just 0 minus 0, which is 0. So the whole limit equals 0. Alright. Okay, these rules are pretty much the same thing as the last rules that we learned, so I'm just going to go ahead and write them down and let you copy them. Essentially, all of these rules apply even when x is approaching positive or negative infinity. The same rules as we learned before. Alright? Go ahead and pause the video and copy all this down, and then hit play when you're ready. Okay, example 3. Find the limit as x approaches infinity of 5x plus sine x all over x. Alright, we can actually split this fraction up. 5x over x plus sine x over x. We know that this is approaching 0. And this one can be simplified. There we go. So let's take the limits of these separately and then add them together. The limit as x approaches infinity of 5 equals 5 because there's no x there. And the limit as x approaches infinity of sine x over x equals 0, that's something we learned in the last example we did with the sandwich theorem. Okay? So, this is what we have. The limit as x approaches infinity of 5 plus sine of x over x equals 5 plus 0. 5 plus 0 obviously is 5. So, this is the limit. Alright, go ahead and pause the video here and try this one. You know, I just realized I have a typo here. It should say find the limit as x approaches infinity of this function and the limit as x approaches negative infinity of this function. Alright, go ahead. Alright, this is one way to solve the problem. I actually used the sandwich theorem again. Sine, once again, is in between negative and 1 and 1. This goes to 0 for both positive and negative infinity, as does this. Therefore, this goes to 0 for both of these. Okay. Alright, vertical asymptotes. As you guys know, vertical asymptotes look something like this. The dotted line here is a vertical asymptote. As you can see, this graph is getting closer and closer to the line, as is this one, but it never quite crosses it. Okay, so here's the definition. The line x equals a is a vertical asymptote of the graph of the function y equals f of x if either the limit as x approaches a from the positive side, like this one, equals positive or negative infinity, or as x approaches a from the negative side, that's like this one, of f of x equals positive or negative infinity. Alright, let's do an example. Find the vertical asymptotes of f of x equals 1 over x squared. Describe the behavior to the left and right of each vertical asymptote. Okay. Alright, let's go ahead and graph this function. We've got 1 over x squared. There we go. Let's change the window. There we go. Okay, so as you can see, as x is approaching 0 from the negative side and from the positive side, they're both going to infinity. So we can write that like this. The limit as x approaches 0 from the positive side goes to infinity. And the limit as x approaches 0 from the negative side also goes to infinity. Oop, it disappeared. Oh well. Okay, so because of that, x equals 0 is the only vertical asymptote. Alright, go ahead and pause the video here and try this one. Alright, this is the answer you guys should have gotten. It looks kind of funny on the graph, but these are supposed to be the vertical asymptotes. As you can see, the limit as x approaches negative 2 from the positive side is going down to negative infinity. Graph disappeared again. Alright, well anyway, you can graph it on your own calculator, the limit as x approaches negative infinity from the positive side is going to negative infinity. The limit as x approaches negative 2 from the, oh, sorry, this should say the negative side. From the negative side is positive infinity, and vice versa for positive 2. So the vertical asymptotes are x equals 2 and positive 2. Alright, next example. The graph of f of x equals tangent of x, which is the same as sine of x over cosine of x. And this has infinitely many vertical asymptotes, one at each point where cosine is 0. And if a is an odd multiple of pi over 2, then find the limit as x approaches a from the positive side of tangent of x, and the limit as x approaches a from the negative side of tangent of x. Alright, let's graph this. Alright, let's see here. So, tangent of x looks something like that. Alright, so, let's see if I can change the mode. Actually, probably want it in radians. Okay, so you can't really see it, but at every pi over 2, at every odd multiple of pi over 2, there's an asymptote. And as it approaches it from the positive side, actually let me see if I can zoom in a bit. Okay, as it approaches it from the positive side, from the positive side, it's going to negative infinity. As it approaches it from the negative side, it's going to positive infinity. And that happens repeatedly for every odd multiple of pi over 2. Okay, so we can write this. The limit as x approaches a from the positive side of tangent of x equals negative infinity, and the limit as x approaches a from the negative side of tangent of x equals positive infinity. Alright, so go ahead and try this one. Remember, cotangent of x, this is the same as 1 over tangent, because most calculators don't have cotangent there. Okay, so go ahead, try that one. Alright, this is the answer you guys should have gotten. And the graph, oh darn, it already disappeared. Okay, well, if you look at the graph, hopefully you guys remember that the graph of cotangent of x is kind of like the graph of tangent. It's opposite, and the asymptotes are every pi instead of every pi over 2. Okay, so as x approaches a from the positive side equals positive infinity, and as x approaches a from the negative side equals negative infinity. So the opposite of tangent. Also, instead of every pi over 2, it hits at every pi. Okay? Alright, let's see here. End behavior model. Okay, so the function g of x is a right end behavior model for f if and only if, remember IFF means if and only if, the limit as x approaches infinity of f of x over g of x equals 1. It's a left end behavior model for f if and only if the limit as x approaches negative infinity of f of x over g of x equals 1. Alright, I'm going to do an example, and then hopefully you guys will understand what this is talking about. Okay. Let f of x equal 3x to the 4th power minus 2x cubed plus 3x squared minus 5x plus 6, and g of x equal 3x to the 4th power. Show that while f and g are quite different for, while f and g are quite different for numerically small values of x, they are virtually identical for the absolute value of x large. Okay. Alright, let's graph both of these functions here. We've got 3x to the 4th power minus 2x to the 3rd power. By the way, this video is going to cut off at some point. And then I'm going to have to go to part 2 because I think I have like 30 seconds left on the clock. Plus 3x squared minus 5x plus 6. And then I have 3x to the 4th power. Alright, let's graph this. Okay, as you can see, when they're smaller, they're very different. but as you go farther and farther out, they look the same.